Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022. And anyway, I'm up to section 3.4 of volume 1 of this series, which is on Fibonacci numbers and the golden ratio. And there's really a lot to say about the golden ratio in particular. And today I'm going to show you what I think is a really cool construction. There's a couple geometric constructions you can make using the golden ratio. There's one thing called the golden rectangle, and there's another thing which is actually very closely related to the golden rectangle called the golden spiral. So I'm going to describe both of these constructions today. So anyway, let's begin. All right, so let's start with the golden rectangle. Well, I already told you what the golden ratio is. It's 1 plus the square root of 5 all divided by 2, approximately 1.618. We use the Greek letter phi for the golden ratio. I guess there's two versions of the letter phi. Here I'm using the standard version, which looks kind of like the empty set symbol. Usually you see the other version. It doesn't really matter which one you use. I just use the standard form of phi here. So here's a golden rectangle is just a rectangle with these proportions. Phi by 1, if you like. And it's kind of interesting because a lot of people say this is the most aesthetically pleasing aspect ratio of a rectangle. And nowadays, I think most TV screens are about this aspect ratio. In the old days, they were more like 1.3 to 1. And I don't think they looked as good. And movies, I think movies have always had an aspect ratio close to golden ratio. That's why a lot of times you see movies letterboxed, or at least you used to when you were watching them on the old TVs, because they want to get the whole thing in there. And they couldn't on a standard CRT screen, which had the wrong aspect ratio. But now that I think TVs have about the same aspect ratio as the old movies or movies they've always had, now they can show them on this pleasing rectangle known as a golden rectangle. And you might wonder why it's such a pleasing looking rectangle. Well, there's a simple reason. You can partition it into a square and another golden rectangle. And this is really just the same thing as a golden section. We're just applying it to a rectangle here. But look what we've done. We started with the original golden rectangle. We partitioned out a square on the left. That's just a 1 by 1 rectangle. And then what we're left with is phi minus 1. But as you know, phi minus 1 is the same as 1 over phi. That's why the thing on the right is another golden rectangle. It's just a sideways one. And there's no reason to stop after one step. You can do the same thing with a golden rectangle on the right and keep continuing. You continue as many times as you want. In theory, you can do it infinitely many times. And here's a construction where this is done 10 times. So we started with a single golden rectangle. We partitioned a square on the left, and then we were left with another golden rectangle on the right. And then we did the same thing. This time we partitioned a square out of the bottom part of the second golden rectangle, and we're left with a third golden rectangle in the upper right. Then we keep doing the same thing, and you can do this in kind of a spiral pattern. Notice that the first square we partitioned was on the left, and the second one was on the bottom. Third one's on the right. Fourth one's on the top. Keep continuing like that. Keep going counterclockwise if you like. And you can do this infinitely many times. I think in this particular picture, this was done just 10 times. And then you're left with a teeny tiny golden rectangle in the middle. I don't think you can even really see it. But anyway, you could do it, infinitely many times if you want. Just take an infinite amount of time. You can't really do anything infinitely many times, but I think you get the idea. And what we and now that we've done this, there's another thing we can do. We can make what's called the goal. It's not actually the golden spiral. It's a closely related spiral. It's going to be called the Fibonacci spiral. So how do we can construct a spiral pretty easily from this partitioned golden rectangle? How do we do that? Well, we have all these squares that are kind of spiraling around this tiny. In the limit in which you do this infinitely times, you have a point in the near the upper right. So we take in this golden rectangle, we've actually partitioned it into infinitely many squares. these squares just kind of spiral around this point in the middle. So we start with the biggest square, that's the one on the left, and now we make a circular arc, a quarter circle, just starting at the upper right corner, going down to the bottom upper left corner, going to the bottom right corner of this largest square. So that's that red arc I'm showing. And now there's no reason to stop with just one square. We can do the same thing for the next square. Now we've got two arcs. And then we can keep going. And we can do this infinitely many times. And when we're done, we're left with this beautiful spiral, this red spiral pattern, which is called the Fibonacci spiral. It's not quite the same thing as the golden spiral, but it's a pretty good approximation. And in the last slide, I'm going to actually show you both of these spirals. The spiral here, I think on this picture, the one in light green is actually the Fibonacci spiral. This is the one, or in yellow, I guess. This is the one that's made up of the circular arcs. But technically speaking, it's not a logarithmic spiral. A logarithmic spiral has the form r equals e to the k theta, where k is a constant. It's the radius is an exponential function of the angle. If that doesn't make sense, you don't worry about it. But that's a technical definition of a logarithmic spiral. And unfortunately, the spiral we just constructed in this picture isn't quite a logarithmic spiral. It's very close, but it's not quite. If you want a real logarithmic spiral, you have to go to the picture in red. And it's very hard to see the difference. I think on this picture, they only differ by less than 1 millimeter at the most. So you can barely even tell the difference between the golden spiral, which is a logarithmic spiral, that has all the same, shares all the same vertices of the squares that make it up, but it just, it's of the form r equals e to the k theta. I don't know what k is exactly. You can calculate it. I'm not going to do it here. But it is a logarithmic spiral. Trust me on that. And just to kind of bring the point home is that the proportions in this picture. I guess for this particular picture, I think I took this one from the web. This is we're starting with a golden rectangle, 1 by phi by 1, length phi, height 1. And then we partition into squares. So the square on the left is a 1 by 1 square, if you like a square whose edge lengths are 1. And then the next one, the edge length is 1 over phi. And after that, 1 over phi squared, 1 over phi cubed, and so on. Anyway, that gives you the construction we just did, the golden rectangle and the golden spiral. So anyway, I think this is a really neat construction. And it's not just of theoretical interest. I'm going to get into this tomorrow, but you actually see Fibonacci numbers in the golden ratio and the golden rectangle, the golden spiral. I don't know about the golden rectangle, but you see the golden spiral, or at least very close approximations of them in nature. Snail shells are very close to this. There's a really cool crustacean called a chambered nautilus. I'll show you a picture of one tomorrow. But the shape of the chambered nautilus is very close to a golden spiral, as we'll see. Anyway, that concludes my video for today on Fibonacci, on the golden rectangle and the golden spiral. So thank you for watching. Long live math, and I'll see you guys next time. Bye.